I have come to recognize that there was another error on exam 2. Weren't any of you mystified by this formula? I'm curious why none of you after the exam didn't come to me to say something about this. In any case, as I said, I'm not going to blame you for goofs that I make. So everybody got credit for this question, because it was really unanswerable as I had stated it on the exam. So regarding bonus quiz 2, question 5, which aims at this issue, change this molecule to this molecule. Okay? Now, as often happens, on further examination of this molecule, which is a radical, it's got an odd number of electrons, by analysis you can recognize that for this molecule the iodine atom is sp3d2 hybridized. But with 4 peripheral atoms, 2 of the positions in an octahedral distribution of valence electrons about the central atom will be occupied for this by 1 non-bonding pair and 1 single electron. So if I propose this having a seesaw geometry, as was stated on the exam, then I can ask this question. Except that seesaw this has 5 different bond angles, which is what I'm asking you about on bonus quiz 2. But if I suggest that this too shows a seesaw structure, then this will show 6 different bond angles for the most polar version. So I'll put that one on a class at some time in the future. This is the way this stuff goes along. Every time I go through this, I find out new stuff. So mistakes are not always horrible. Oftentimes you learn more from mistakes than from anything else, because you have to think about what's wrong with this damn thing and how can it be reconsidered to be made right. So change bonus quiz 2, question 5 to refer to this molecule rather than this molecule. But if any of you want to tackle this on the basis of what I've said here for the most polar version, come and talk to me about it. It's the fun of the game. Now back to what we said about wrapping up chapter 21. Again, illustrating an important use of the information which is contained in table 1, thermodynamic properties data table. A table which I have said contains more chemical information than any other single table. Should you go on to be a student of chemistry, you'll realize this, I would hope. As an example, we recall once again that in our acid-base table we did not list K values for the strong acids other than hydronium ion. And all the other strong acids in the table are stronger than hydronium ion, which means at the minimum they'll have bigger K values than 55.5, which is Ka hydronium ion. How might we get those Ka values? You're hard-pressed to get such values by direct measurement in water solution, because these things are ionizing 100%. You're not going to have an equilibrium molarity of the unreacted acid to measure. At least not one which you could likely measure, because its molarity, because the molarity value would be so daggone small. Well, let's pursue this further and use the information in Table 1 to get Ka values for our very strong acids. Nitric acid is what I asked you to think about. From Table 1, you see delta G sub F super 0 for pure nitric acid, which at 25 centigrade is a liquid, and for nitrate ion AQ. Of course, the table also contains delta G sub F super 0 for water liquid and hydronium ion AQ, but we don't need to include that in this arithmetic because delta G sub F super 0 for this equals delta G sub F super 0 for this. So that comes out in the wash when you apply Hess's law to get delta G 0R for this reaction, which is this value, from which we use this relationship to get Ka, which chemically is this. We do the arithmetic, we get that. How many of you did this? I told you to do it. At least you're honest. For the life of me, I wonder why. I mean, it isn't just you. I see all classes doing this. I'll pose a problem and I say, I expect when we gather together the next time, you'll know how to do this. It's the case that almost no one ever does this. I don't know why. Now, if I was to do something nasty like say, okay, we're having a pop quiz. You got 5 minutes to answer this for 50 points. And if you don't, it's minus 50 points. Woo! Would things change then? Because I know how students operate. You can cuss, scold, stomp your feet, jump up and down, holler, all you want. Unless it involves points, students don't give a damn. That's not the way it should be. What you should care about most of all is learning. But it's really not your fault. You've been trained to behave like this. And now you run into a screwball who expects you to behave differently. A screwball, of course, is me. But I'll argue that my way is the best way. Because it will lead to your betterment. That's what we want. Any case, enough of the scolding sermon. Let's proceed. From this, because this will be x 1.0 minus x, because under standard state conditions, 1.0 plus x, 1.0 plus x. Under standard state conditions, these are all present at molarities of 1.0. So you start with that, and then you calculate the equilibrium values. And with this K value, you can recognize that practically all of this will do what? Be there or disappear? Disappear. Which means these molarities will be effectively 2. And this molarity will be effectively 0. You do the arithmetic, you'll get this. That's pretty small.
Why is it 1.6?
We're starting with this under standard state conditions. Remember? Standard state conditions. All system components are present under standard state, in the standard state. And for solution species, that's 1 molar. So we're imagining if we start with this system under standard state conditions, what will be the molarities for each system component when we get to equilibrium? We've just done that. If you take data from table 1 and do the same arithmetic so as to get Ka for sulfuric acid, what kind of Ka value will you get compared to 8.2 times 10 to the 4th? A larger value. Why?
Stronger acid.
Yeah, I mean, if you believe what we got in the table, you see sulfuric acid is a stronger acid. I got it scribbled here someplace. My memory's right. Ka sulfuric is on the order of 10 to the 11th. Let's see, 3.6 times 10 to the 11th. I get it. If you want, you can take the data and do this arithmetic and see if you get this K value. So talk about a tiny equilibrium value for the molarity of sulfuric acid in initially 1 molar sulfuric acid solution. See, practically speaking, there's not going to be any sulfuric acid left. Now, if I do this to get Ka for HCl, if the information in the acid-base table is correct, on a qualitative basis, we've shown with the listing of HCl relative to nitric and sulfuric that HCl is stronger than nitric but weaker than sulfuric. So we should expect to get a K value that's intermediate between that for sulfuric, smaller value Ka for HCl than sulfuric, but larger than that for nitric. I get 2.0 times 10 to the 6th. Now, there is a difference, however. Calculating the Ka value leads to no difference, but the difference is in dealing with the in the hydrochloric acid solution, is that under normal laboratory conditions, this stuff is vapor phase. So now you have to recognize that the equilibrium constant which you calculate will have what units? I'll put here U's. You got m squared over p, right? M squared is moles per liter. And p's in atmospheres. Given the data in our table, I think corresponds to measurements made with gases under pressures of atmospheres rather than bar. So if we're going to operate with this, we got a unit problem. So if I pose the question for my hydrochloric acid solution, under initially standard state conditions, what will be the equilibrium molarity of HCl, the unreacted, representing the unreacted HCl? Well, I got a problem here because this thing is in atmospheres. But I know that HCl is quite soluble in water. So proposing a system composed of hydronium ion and chloride ion in water solvent at molarities of 1.0, above which we have a partial pressure of HCl at 1.0 atmospheres, is hypothetical at best. You can't create this system because the HCl is going to dissolve in and react with the water immediately. But if I do this calculation using thermodynamic information, that's what I get. Molar concentration times molar concentration divided by pressure in atmospheres. So if I want to relate this to HCl molarity at equilibrium, if I want to relate it to this, then I got to establish relationship. I must establish a relationship between HCl, whose concentration is measured as a function of pressure, to HCl, concentration measured as a function of moles per liter. So I'll write this. How can I get HCl initial molarity equivalent to partial pressure of HCl at 1.0 atmospheres? Standard state equivalence. Based on ideality, I'll take HCl to have a behavior describable by PV equals nRT. For this crude approximation, good enough. So N over V is P over RT. I just took PV equals nRT and rearranged it, because N over V is concentration in moles per liter if the volume unit is liters. I put in the information, I get 0.041 molar. So at equilibrium, this is hydronium ion molarity times chloride ion molarity, which are each 1.0 plus X, just like we had over there for the nitric acid solution in the numerator. divided by 0.041 minus x. And before I do any arithmetic, with this k value, how will x compare to 0.041? How must x compare to 0.041? About half 0.041? A lot smaller than 0.041? Or practically 0.041? How must x compare? Got to be in essence 0.041, and to two significant figures it is 0.041. So I'll have to stretch my significant figures to see what I can come up with. And here's what I come up with. Equilibrium partial pressure of HCl gas 5.4 times 10 to minus 7 atmospheres, and HCl equilibrium 2.2 times 10 to minus 8 moles per liter. Pretty damn small. You can do the arithmetic for your own benefit. What counts is, I think, to see how these data from Table 1 can be used to approach problems like this. That's what we've shown. So now we'll take a look at a couple of the challenge problems. This was a challenge problem. This is challenge problem number 1. You've noticed, I'm sure, that at the tail end of each chapter in the notes, there are usually some challenge problems offered. Problem 21.2 relates to a question which chemists are still wrestling with today. And that is, what is the true nature of the hydrated proton? Well, maybe I'm being naive about this and missing some important considerations, but no matter how much I've thought about this, it strikes me that the only formula which is reasonable that can be written for the hydrated proton is this. Not this, or this, or this, or anything else. Yet arguments are still going on in chemistry. I mean, here's H plus with this huge positive charge density. So will it, on a time average basis, have 2 water molecules stuck to it, which gives us this, 3 water molecules stuck to it, which gives us this, 4 gives us this, or only 1, that's the hydronium ion? I mean, there's no question from a charge density standpoint that we could well expect these extensive degrees of hydration of H plus. But let's take a look at some chemistry which we discussed in brief at the end of chapter 19. You remember that? Lewis acid, Lewis base stuff? We recognize that if we consider the formation of the hydronium ion, it comes about as a consequence of this reaction. This is the Lewis acid. This is the Lewis base. The water molecule has 2 non-bonding pairs on its central oxygen atom, which illustrates its capacity to behave as a Lewis base. H plus under no circumstances could be a Lewis base because it has how many electrons? Not at all, none, any, zip. But how many coordinate covalent bonds can H plus make? That relates to the number of empty valence orbitals which it has, does it not? Isn't that the feature of a Lewis acid? A species with 1 or more empty valence orbitals. Well, how many empty valence orbitals does H plus have? How many? 1. It lives in energy level number 1. Period 1. It has a maximum electron capacity of 2. That's it. So when this damn thing makes 1 coordinate covalent bond, its electron capacity has been saturated. Well, to me, that means that hydronium ion, that's it. You made 1 coordinate covalent bond, which puts 2 electrons into the valence environment of H And you can't go past that. Not if you believe these fundamental considerations which come to us from quantum mechanics. And yet it's the quantum mechanics people who are arguing about this. Well, as far as I'm concerned, they can carry on with their arguments. And I'm sticking with hydronium ion, and on we go. Problem 21.3. Recall, if you will, that what you did in discussion class. Was A, to consider the decomposition of calcium carbonate into calcium oxide and CO2, first at NLC, normal lab conditions, for which you got a K value on the order of 10 to the minus 23. And if you paid attention to the arithmetic which was shared with you regarding this issue during discussion class, you found out that if I take a 10-liter flask, a pretty big flask, and take from it all the CO2 molecules, I don't care about any other molecules which might be in there, but I want any CO2 molecules in there. And then I place in the flask under normal laboratory conditions, in this flask with no CO2 molecules, some calcium carbonate, and then seal the flask. What will happen? Will the calcium carbonate decompose spontaneously in accord with this reaction equation? Calcium carbonate in a flask, 10-liter volume. The flask initially contains 0 CO2 molecules. What will happen to the calcium carbonate? Will it decompose spontaneously in accord with this transformation? Yes or no? Yes. And it decomposes spontaneously until you put how many CO2 molecules into this 10-liter volume? You did that. 6. Oh boy, 6 CO2 molecules. 1, 2, 3, 4, 5, 6. You think in every 10-liter volume of this air atmosphere, I might be able to count 6 CO2 molecules? There, I'll count a hell of a lot more. Since CO2 is a natural human respiratory product. Upshot, is this stuff going to decompose by way of that reaction in this room? Hell no. Put another way, if I now introduce into this room calcium oxide, I bring in some pure calcium oxide, would you bet that calcium oxide is going to reach into this atmosphere and scavenge CO2? And convert to calcium carbonate in so doing? You're damn right. But you took this further and said, let's imagine this decomposing under standard state conditions. Well, as soon as I say standard state conditions, that means consider this reaction taking place when the partial pressure of this is how much? 1 atmosphere. And you found out, yes, that'll go if you jack up the temperature to about 1100 Kelvin. And to my knowledge, since calcium oxide is a very important industrial chemical, I don't know how many tons of it are made per year, but a hell of a lot by the American chemical industry, and I'll bet they make a lot of it here in Florida because Florida's subsurface, geologically speaking, is rich in calcium carbonate deposits. And this is telling us if I get the calcium carbonate to decompose, I can expect to get calcium oxide. So I'll bet they're making a hell of a lot of this calcium oxide right here in Florida. I know there were industrial concerns in the Tampa area, which do a lot of calcium carbonate chemistry. They also do a lot of calcium phosphate chemistry. Make fertilizers, a lot of things. Well, problem 21.3 says, what about getting this stuff to decompose spontaneously if the partial pressure of CO2 gas is 1 times 10 to the minus 3 atmospheres? Because when the partial pressure of CO2 gas is 1 atmosphere, which is what you were asked to consider regarding this transformation in discussion class, then this relationship applies, does it not? If the partial pressure of CO2 is 1 atmosphere, this relationship applies to this transformation, correct? You did this in discussion class. Did you realize this? Because if the partial pressure of CO2 is 1 atmosphere, that's the value for the equilibrium constant, because the equilibrium constant for this thing is P CO2 gas. And you use, what the heck is it? There it is. Delta G0 equals minus 2.3 RT log K. If K is equal to 1, well then, delta G0 is equal to 0. Which means delta G0 is, which means delta H0 for the reaction is equal to T delta S0. So you can calculate the temperature. That's what you did for the standard state condition. But problem 21.3 says, let's imagine the partial pressure of CO2 is 1.0 times 10 to the minus 3 atmospheres. How do you get the temperature for this to take place? Well, the first thing you should recognize is the temperature at which this reaction, right here, will be spontaneous in an atmosphere of CO2 for which the partial pressure is 1.0 times 10 to the minus 3 atmospheres. How must the temperature for this transformation corresponding to these conditions compare to the temperature that you determine for this taking place under standard state conditions? Temperature must be, why?
Because it doesn't have to get the system as much. There's less carbon dioxide, so you don't have to, I don't know how to describe that.
Well, we found out with what you did in discussion class. If you run this under normal lab conditions, you get a partial pressure of CO2 on the order of 10 to the minus 23 atmospheres. Remember that? And if you want it to be 1 atmosphere, partial pressure of CO2, you had to jack the temperature up to about 1100 K. Well, now I want to jack up the partial pressure of CO2 to 10 to the minus 3 atmospheres. Well, that's got to be bigger than normal laboratory temperature of 298 K, but smaller than this 1100 K. That's the kind of stuff you want to think about before you start grinding. How do I get the value? I just apply this. You've got delta H0 value for this reaction. You've got delta S0 value for this reaction. You want the T. And what am I going to put in for K? Or more to the point, what am I going to put in for log K? What's the log to the base 10 of 10 to the minus 3? What is it? Minus 3. Done. Do the arithmetic. And so we go to electrochemistry. And in so doing, continue with our adventures into chemical thermodynamics. Because all we've done this term is chemical thermodynamics, and that's all we're going to continue to do. Because the analysis of reactions and their progress from a kinetic standpoint much more difficult, much more challenging. Beyond the scope of what we could effectively achieve in first-year chemistry. There's some things we can do, but not nearly as much as we can do with the thermodynamic analysis of reactions and their progress. Working definition of electrochemistry. The study of redox reactions, both qualitatively and quantitatively. The simplest way, I think, to define redox reaction is a reaction in which atomic oxidation numbers change. Now, you learned in 2045 about how to assign oxidation numbers, didn't you? How to determine them. Unfortunately, at the time in which this is offered you in 2045, it's offered in relationship to learning some fundamental aspects of chemical nomenclature. But about the only device you could rely on at that time was called memorization. An unfortunate way to learn things. Because it does not necessarily invite understanding. The very best way by far though, to get at oxidation numbers is to A, recognize that they are based on relative, what? Relative what?
Charge.
Nope. On what atomic property?
Electronegativity.
Electronegativity. That's what. That's what oxidation numbers depend on. So we'll keep in mind electronegativities and perform Lewis structure analysis to get at oxidation numbers. How do we play this game? Let's talk about three species. The nitrate ion, the acetic acid molecule, and the histidine molecule, an amino acid. Think amino acids are important? Well, if I said that we're going to do this by Lewis structure analysis, then I expect you to be writing Lewis structure right now as we talk. Let's go, quick, boom. At least for these two. And while you do these two, I'm going to put the histidine molecule on the board. Everybody got nitrate ion? Everybody got the acetic acid molecule? The acetic acid molecule's typed formula shows you one of the difficulties that we have in trying to communicate chemical structure by writing formulas. Because this is a carboxylic acid. But writing the formula suggests that it's a peroxide where you've got oxygen-oxygen bond. Not true. I told you this in the lab manual in 45L for assignment 6. Anybody remember that? If I were to put this on a quiz or exam, I'd tell you no oxygen-oxygen bonds to steer you away from believing this is a peroxide. Now then, after we have the Lewis structures, and you know I've already told you this, that I have a disdain for using dots as non-bonding pairs. Nothing wrong with it, it just takes longer to draw. After we have the Lewis structures, we go to each bond site. What's a bond site? You know that? If I use language like this and you don't know what I'm talking about, then we're not getting any place. Bond site, bond site, bond site, bond site, bond site, bond site, bond site. You know, each place where the Lewis structure shows shared electrons, bonding electrons. That's a bond site. You go to each bond site and you parcel the electrons so as to give the electrons at the bond site entirely to the atom of greater electronegativity. So let's parcel the electrons at the NO bond sites. That was easy, because O is more electronegative than N. Let's do the same for the acetic acid molecule, keeping in mind, as I'll bet you know right off the bat, when I have bonding electrons between identical atoms, how do I divide up the bonding electrons? How? How? Homolytically. That's right. Homolytically. Equally. Take the number of bonding electrons, divide by 2. This atom gets half, the other atom gets the other half. So let's go to the bond sites. And play the game. Now, after we've got the electrons parceled, we apply a rule. The rule is to calculate oxidation number, which I symbolize with capital O wrapped up in parentheses. This means oxidation number for the work we are presently considering in chapter 22. Okay? Equals. Recipes in the notes. The number of valence electrons which the atom in question has as an isolated atom, an atom all by itself. Well, we go to our periodic table. Carbon. How many valence electrons carbon atom have? 4. Oxygen? 6. Nitrogen? 5. Bingo. All you got to do is pay attention to the family number. Next reminder. This game only applies to A family atoms, because when you get to the B family atoms, you're talking about atoms which have a mixed bag of valence electrons. So you won't find games like this applicable to species which contain transition metal atoms as constituents, components. All right? Nitrogen, 5 valence electrons. And after you've played the parceling game, you take the number of valence electrons which the isolated atom has, that we've shown you comes from the periodic table, and subtract from this the number of electrons which the atom has in the Lewis structure after you have parceled the electrons. How many does nitrogen remain with? Not any. So nitrogen oxidation state in the nitrate ion is +5. Oxygen, 6 minus 2468. 2468, 2468. They're all, each oxygen, I hope you recognize, is now electronically equivalent. Because after I parceled each electron, each oxygen atom has got 8 valence electrons. So we've recognized each oxygen is -2 from an oxidation number assignment standpoint. Nitrogen is +5. So if I add up -2 to -2 to -2, I get -6. And add that to +5, what do I get? Is that not equal to charge on the species? Bingo. That's one way to check whether or not you did this arithmetic properly. Let's play the game for acetic acid. Now, oftentimes I've seen textbooks ask questions like, report the average the average oxidation number for carbon. That's pretty dumb. We'll see why in just a second. We've parceled the electrons. H is +1. Because after parceling for the species, each H remains with no electrons. So 1 electron less 0 is +1. And you know the most common oxidation state shown by hydrogen in its chemistry is +1. 0 if it's bound to itself. And under what circumstances does hydrogen show a negative oxidation state? When it's bound to an atom which has a lower oxidation state than hydrogen itself, like metals in forming hydrides. You heard about those, haven't you? Like NaH, sodium hydride. Sodium's +1, hydrogen -1. Well, back to this. Each H is +1. The oxygens are -2. But let's take a look at the oxidation numbers for the carbon atoms. Let's look at this carbon. Let's call this carbon 1 and this carbon 2. Well, let's put this 1 in here. C1 equals 4 less 2, 4, 6, one more 7, minus 3. Carbon 2. Four less 1. That's it. Plus 3. Now, why does this analysis have a direct bearing on the chemistry of this molecule with respect to the component carbon atoms, whereas reporting an average oxidation state of carbon as 0 for this thing is kind of stupid? This analysis supports the conclusion that this carbon bears a far greater negative charge density than this carbon. Minus 3 compared to plus 3. Which means if this molecule reacts with an electrophile, woohoo! Electro for electron. What's phile mean? Philo. Loving or attraction. So an electron-loving species reacts with either of the carbon atoms in the acetic acid molecule. Which carbon atom do you think it'll choose? Carbon 1, carbon 2. Carbon 1 or carbon 2? Electron-loving species. Carbon 1. This analysis shows you this is much more electron, has a much greater electron density than carbon 2. A benefit of this analysis. But if a nucleophile attacks one of these carbon atoms, it's going to hit this one. Nucleophile. Nucleus loving. It's looking for something which is from a charge from a relative charge standpoint, plus or minus. Nucleophile. It's looking for positive. Nucleophile. In the nucleus we find protons, don't we? So this shows you the chemistry of this. Now then, I've taken the liberty here of having given you the Lewis structure for the histidine molecule. You know, I used to say, well, look it up. Well, hell, you can look it up just like I can look it up. You can find this on, we'd Google in about, what, 3 seconds? Histidine, boom, there it is. Wikipedia will have it all over the place, plus other sites. You take this and analyze it for the oxidation state of every carbon atom. It's not hard. We've shown you how to play the game. But in so doing, you'll recognize that only 2 carbon atoms have the same oxidation number. And the carbon atoms for this molecule range in oxidation number from plus 3 to minus 2. What I just said is in the notes. Carbon atom oxidation number range is plus 3 to minus 2. And you got 1, 2, 3, 4, 5, 6 carbon atoms. And only 2 of these carbons have the same oxidation number. So play the game. And now, as a peek to the future. See this ring? 1, 2, 3, 4, 5 atoms in this ring. N, C, N, C, C. See this ring? Okay. We'll do stuff like this in chapter 23. Is this ring aromatic Whoo, what the hell does that mean? Doesn't mean does this ring stink. If you don't know what aromatic means, look it up. It's a relationship to resonance. You think this ring shows resonance? You think about it. Now let's ask one more question. You see these two nitrogen atoms? Each one, based on the Lewis structure, has a non-bonding pair. It's all right over here in the question. Which ring N atom is more basic? Two N's in this ring. Which N atom is more basic? We'll pick it up from this point next time.